News.
Thank you everybody for coming out tonight for our final lecture of the Fall 2016 lecture series. Much to the chagrin of some people in the audience, but we will be back in the spring, not to worry.
Yeah. Who is coming to their first Science in the News event? That's awesome. Welcome. We hope this won't be your last. We are taking, as Steph said, a brief, 5-month respite after this, but we will be back in the spring, and in the meantime, we have a ton of other things going on. So for those of you who are new and for those of you who are old and want to hear this again, I'll just give you a brief overview of what Science in the News is all about and who we are. So Science in the News is a graduate student organization based here at Harvard. We draw from student population across all 11 schools of Harvard's graduate schools. And we have two main goals as an organization. The first is to clearly and effectively communicate cutting-edge science topics to the general public. And the second is to train a new generation of graduate students to better communicate their science. And this lecture series is definitely one of the cornerstones of our organization. Even though it's coming to a close, we have a lot of other endeavors that we will continue to pursue throughout the year, not on the schedule. So the main thing that I want to advertise tonight is we have a couple more Science by the Plate events going on. These occur in Somerville at the Burren in Davis Square, as well as at Aeronaut Brewery. These are events where local science faculty members come with their labs, do an informal Q&A, so you can head over there, grab a beer, and chat with scientists. We also have our online blog that I encourage you to check out at sitinboston.com. We are now publishing 4 or 5 times a month, so please check out our articles. We publish on a really wide range of topics. Most recently, we published a special edition entitled Dear Mr. President, which highlights some of the topics that we think our future president should know with regards to the science world. And
on that note, we're also excited for you to be here tonight. Just to give you an idea of what to expect, we have 3 wonderful speakers. They'll be giving the talk in 3 parts. The first 2 parts followed by a brief 10-minute intermission. Additionally, Katie and I are going to be moderating the talk, so we'll help the speakers move along during question section. So if we have to, limit questions at certain points, don't worry. You'll have time during intermission and after the talk to speak to our speakers some more. And I also want to put in a plug for our survey here. This is really helpful for us in planning additional events. You can give us suggestions on other topics you want to hear about, and also give us feedback to our speakers for tonight. And so with that, we will let Catherine take it away.
Hey everyone, I want to reiterate that thank you for coming and listening to our talk tonight that's entitled From Ebola to Zika, Combating Myths and Controlling Mosquitoes. My name is Catherine Friege, and I'm a second-year PhD student here at Harvard in the program in virology. And I want to start you guys off with this image. Many, if not all of you, may be familiar, but this image is very characteristic of the current viral outbreak that's happening right now in Brazil, other parts of South America, as well as Central America, and even impacting parts of the United States. And this picture shows you a child that was born with microcephaly. And microcephaly is a birth defect in which a baby's head is significantly smaller than one compared to a baby's of the same age and sex. And this condition often can lead to speech and movement development delays, blindness, seizures, and just general difficulties later on in life. And so this birth defect has been a good image in terms of this outbreak because of the fact that Zika virus has been connected to this birth defect. And so today, in our talk From Ebola to Zika, I'm going to touch in the first section on basically give you guys an introduction to viral outbreaks, of Viral Outbreak 101. And then Shirley and Kelsey are going to talk to you about virus transmission and mosquitoes and viral disease. So to start you out, I want to address this question of what exactly is an outbreak, a viral outbreak. And the definition of outbreak is when cases of a disease are in excess of what would normally be expected in a defined community, geographic area, or season. And this is why something like flu during the winter or the common colds that you get during any time of the year aren't considered outbreaks or viral outbreaks because there's always going to be some normal level of disease in our communities or at a certain time of the year, such as this winter season. And so an outbreak has to be some level of incidence above that baseline or normal of what we expect. And then two other definitions that I just want to talk to you guys about are epidemic and pandemic, which can be related to this definition of outbreak. And so an epidemic is considered a widespread occurrence of disease in a community at a particular time. So this is something like the Ebola outbreak in 2014, because it was an outbreak of disease that occurred in a particular community at that time. And then the other definition is of a pandemic, which is when a disease is prevalent over a whole country of the world. So an example of this would be something like the 1918 flu or the Spanish flu, where we saw an increase in flu cases across the United States as well as parts of Europe that coincided with World War I. And so with all of this, we have to think about where are we getting information about outbreaks that are occurring in our communities or across the world. And one of the most common resources we use is the news media, either on television or in print. And so one of the things that the news media uses to convey outbreaks are imagery. And so I wanted to show you these three pictures, either whether it's a picture of the Ebola virus, or a picture of a mosquito biting a person's arm, or a picture of either medical doctors or scientists suiting up in this ear. And I don't know about you guys, but this kind of looks scary to me. And so when you think about how the media is sort of lashing you into reading about outbreaks or making you think about what's happening around you, these images can be pretty scary. And so you have to sort of step back and think about the true facts of what's happening in a current outbreak. And the other thing that goes side by side with these images is the type of language that's often used in headlines in the media. And so I wanted to just give you guys some examples from the 2014 Ebola outbreak of things that we were seeing as headlines from news sources like the New York Times or NPR or the Los Angeles Times. And so words like exposed, or if you remember the nurse that was quarantined in New Jersey, things like defying or even just the word quarantine. And also a more recent article in NPR from just last week from new research where they use words to describe Ebola like mutant and explosive. And so all of these words are great at making us click on these articles and read about them, but they're pretty hard-hitting, scary words. And the other article that I wanted to bring to your attention, mostly because it has a personal story for myself, is this article from the New York Times, Can You Get Ebola from a Bowling Ball? And I actually lived in Brooklyn, New York at the time of the Ebola outbreak, and I lived not very far from this bowling alley, and actually coincidentally happened to be at the bowling alley the week before this doctor who had been helping with the Ebola outbreak in West Africa had gone to this bowling alley for a party and then came home from the bowling alley and started to get the symptoms of Ebola, the high fever. And so I remember initially thinking, oh my gosh, this was so close to home. This is very scary. That who knew that Ebola could be right in my backyard? And thinking, initially being very scared, but then remembering the ways that you can get Ebola, which is through direct contact with the fluids, which Shirley will talk about in her section of the talk, and thinking, this article is not as scary as I originally would think, and that I can't in fact get Ebola from a bowling ball. And so if we think about the way the media talked about the Ebola outbreak in 2014, that brings us to what's happening right now with the Zika outbreak. And there are a couple of things that I want to touch on that were that make the Zika virus outbreak very newsworthy. And so the first of those reasons is that Zika was considered or labeled in the beginning a new virus, but I have new in quotation marks because it actually isn't new. And I'm going to talk about that a little bit later in my section. And because Zika is an understudied virus, we don't have a vaccine or treatment or any sort of drug treatment for this disease. And so this is something that the entire scientific community as well as pharmaceutical community are sort of putting all hands on deck in order to develop a vaccine or develop some sort of treatment for Zika virus at this time, but it's something that we do not have at this moment. And then the other thing, which I showed you earlier, is that Zika virus can lead to microcephaly if a pregnant woman is infected. And this is interesting because when Zika was first identified in Brazil, like most of the symptoms are what you would expect from flu. You get a high fever, some fatigue, rash, but for most people, they actually don't even see any symptoms. And so it's less concerning than, say, the Ebola outbreak, where the disease was so fatal for a lot of individuals. But when we started to see this increase in microcephaly in Brazil, that basically raised the idea that this was a bigger health concern than we originally thought, that there were more implications besides these flu symptoms, particularly for pregnant women. And then the last thing, which I'm sure most of you are familiar with, is the timing and the location of the Olympics in 2016. So Brazil was the center of this outbreak, and yet in 2016, we were slotted to have the Summer Olympics there. And so this brought a lot of questions about whether athletes were going to want to travel to this area, whether spectators were going to come and watch the sports. And then also, I remember hearing questions about, do we even want to move the Olympics? Because we didn't know much about this virus, and we didn't know what the implications were. And so these were all questions that sort of made this viral outbreak sort of primed for the media representing it in a certain way. But in contrast to how we represented outbreaks in the media with Ebola, we've been improving the way we're using our language. And so I want to show you two examples of some recent headlines in the New York Times about Zika. So I'm going to talk about this later, but Zika actually has been identified in Florida, specifically the Miami area. And so instead of using things like mutant or explosive, we're saying things like, but it's no cause for panic, scientists say. Or also defining articles by presenting the facts, which is the most important thing, is knowing, understanding what we know and what we don't know about this virus. And that's what we should all be thinking about when we're thinking about viral outbreaks. And so one other resource that's excellent at doing this, at conveying the facts about what we know and what we don't know, is the Center for Disease Control, the CDC. And the CDC is a government organization whose main goal is to inform the public, do research, and also basically provide management for diseases across the United States and globally, whether this is bacterial diseases or viral diseases, or diseases that we encounter on a day-to-day basis, like cardiovascular disease or different mental illnesses. And so the CDC is one of the great resources that can provide us with the facts about what we don't know. And on their website, they have tons of infographics like this one, where they tell you just what we know and what we don't know. And I wanted to highlight a couple of these from this particular infographic, which is that we do know that Zika can be passed from pregnant woman to her fetus. And we also know and have been getting increasing evidence that infection during pregnancy can cause certain birth defects, like microcephaly. And we also know that mosquitoes that can carry Zika are actually found in some parts of the US, which Kelsey will talk more about in her section of the talk. But then at the same time, the CDC also does a good job telling us what we don't know. And these are two more travel-related facts that just exemplify that we don't know much about the safety of travel to areas that have Zika virus. So we don't know if there's a safe time during pregnancy to travel to an area with Zika. And we also don't know if you travel and are bitten, how likely you are to get Zika virus, but also how likely it is that your baby can get the birth defects from the infection. And so these are two sort of more general travel-related unknowns, but there are many unanswered biological questions that researchers are currently quickly working on. And so all of this sort of brings me back to this idea, the question that I have, which is, are viral outbreaks becoming more common? I talked about the Ebola outbreak in 2014, and then Zika first starting in 2015, so just a year later. And so I want to touch on the fact that if you look at viral infections starting from the early 19th century, they were much less frequent. So smallpox, there's a smallpox outbreak in Boston in 1901, and then fast forward a little bit, I talked about 1918 flu, which was a flu pandemic in the United States and parts of Europe, and then in 1984, HIV was first identified. And this is not a comprehensive list, but just to get you guys a picture of how much things have changed in the last few years. So in 2003, there was a SARS outbreak in China, and then quickly followed by MERS, H1N1, which was swine flu, and the Ebola outbreak in 2014, and now Zika in 2015. And so the question that I always have is, why is this happening? Are there more outbreaks, or are we just, or is it context dependent? Are we able to travel to more places, and therefore we're interacting with different people and different animals that we weren't necessarily seeing before? Or is it because we can travel to new areas and thus identify and diagnose outbreaks that we weren't able to before? And so to sort of illustrate how much we're traveling now, I have always found this picture very striking. And this is the global flight paths of airlines in the world. And you can see from each of these green tracks that areas like the United States as well as Europe are almost completely covered in green. And so this sort of hammers home that point that we're able to go to more areas more readily, we're able to interact with individuals and populations that we weren't necessarily able to interact with many years ago. And so all of these things could be influencing this sort of uptick in the number of viral outbreaks that we're seeing. And it's important to know that this is one of many, many factors that are impacting these number of viral outbreaks, that it's not just globalization, it's not just improved diagnostics. It's a very complicated story, but that's just something that I wanted to highlight. So with that, I'm going to take a quick break for questions.
You did a good job presenting that a lot of times the media is way too dramatic in their language. But let's say like the 1918 Spanish flu breaks out again. You know, how will I know that like, oh, this is actually something really serious?
So the question was, you said that the media does colors outbreaks in a certain way, but if say the 1918 flu pandemic were to happen again, how would I know that something is serious? And I think this sort of brings me back to my point about the CDC. So the CDC as well as the WHO are really geared to sort of make statements and predictions as well as give good advice about what you should be paying attention to. They'll often report how many incidences are happening in certain areas. And so that is a good sort of resource to turn to that's supposed to be less biased than the media.
So, we talked a bit about the Olympic Games and all of its leading up to the Olympic Games. Was there any kind of analysis done afterwards to see if any of that came true, or what any consequences, or follow-up outbreaks there were?
That's a great question. So our question is, I talked about the lead up to the Olympic Games and how there was a lot of concern about whether or not it was a good idea to have the Olympic Games in Rio. And whether or not there was any analysis done. I'm not extremely familiar with the analysis that has been done, but I have seen reports they've looked at whether the incidence of microcephaly or increased travel-related cases of Zika infection there has been an uptick since right immediately following the Olympics, and it's sort of difficult to disentangle that sort of information. So that's something that I would love to learn more about as well, and I know that research has been done.
This may be a better question for speakers after you, and if that's the case, please let me know. Just this morning, I heard on the radio, and you don't know if you believe everything you hear on the radio, I know, but that the Zika virus spread faster, and there were more cases per unit of people or area or however that's measured in Brazil than the places where they think it came from. A, is that true? And if that's true, what would account for that other than the fact that it was new there and whatever things might hold it in check there that it had been in places where it came from?
So I'm going to talk about that a little bit. So I'll repeat the question. So he asked, he had heard on the radio that there was sort of research that came out that the virus was spreading faster in Brazil than it had done in previous places. And that is an excellent question. So my answer to that, and I'll talk about it a little bit later, is that most of the epidemics or instances of Zika virus before were confined to sort of small areas. And I think in my opinion, I mean, that the outbreak in Brazil happened in a very population dense area, and so that sort of could be a factor in leading to increased effect size. But again, it's a complicated story, and I think Shirley and I are both in a lab that's interested in viral genomics and whether or not the actual genome of this new Zika virus is much different than the previous ones that we've identified. And so I think scientists are, now that human data is coming in, are going to be able to answer that question hopefully more readily. Great. So as I continue, that's actually a good springboard for the next part of my section, which is talking about why Zika virus is not actually a new virus. So I mentioned this a little bit in my answer to Audience member's question, is that Zika actually isn't new. That the first detection of Zika virus actually occurred in 1947 in Zika Forest, which is in Uganda, and where the name of Zika virus actually came from. But this instance was mostly confined to primates and also primate handlers, and so we didn't really see very much happening from this first detection. And then in 2007, so not that long ago, was the first epidemic of Zika virus. And so this, on this island, Yap Island in Micronesia, there are only about a couple hundred cases of Zika virus. So again, the population was probably pretty small in that area, less chance for it to spread to many people. But then in 2015 was the start of the current Zika outbreak in Brazil. And so again, this is just to make the point, this isn't a new virus, it's actually been around for quite some time. And so I'm going to talk to you guys a little bit about Zika prevalence in the United States, but also how sort of this virus has been impacting Brazil and other parts of Central America, and has become sort of more of an issue in the United States. But the thing that I want to talk to you first about, and Shirley's going to go into more detail about this, is this balance between different types of transmission. So in the United States, we're actually seeing more travel-related cases. So this is the idea that you travel to Brazil on vacation or for the Olympics, you get bit by a mosquito in Brazil that's infected with Zika virus, and then you come back to the United States and start to get those flu-like symptoms, fever, rash, fatigue, and then you go to the hospital or your doctor, and then you get diagnosed with Zika. And so this gets sort of a tick mark in a United States case of Zika virus, but it's actually not local, it's a travel-related case. And then the other side of that is this idea of local transmission. And this is what's mostly happening in the areas like Brazil and Central and South America, where most of the transmission that they're getting is either through person-to-person contact, like sexual transmission, or through the bite from a mosquito. And so it's important to think about that when you hear about the number of cases of Zika in the United States, that most of what we're seeing is actually travel-related. And so we go into more detail about how sort of this virus and outbreak has grown over the start in May of 2015, which was the first instance of our first identification of Zika in Brazil. And then in October of 2015 is when Brazil started to pay more attention to this outbreak, because as I said earlier, the symptoms for the disease are mostly just flu-like symptoms, and so we weren't that nervous about it compared to other viral outbreaks or other viruses that are in this area. And so, but in October of 2015, Brazil started to see increased cases of microcephaly, and this is where they started to raise a red flag, like maybe these two were connected. And then just a month later in 2015 was the scientists first detected Zika in a newborn child. And so this sort of more solidified the causative relationship between the Zika virus infection in a pregnant woman to the effects, to the birth of a child with microcephaly. And then just a month later, in December of 2015, we got our first local case of Zika in Puerto Rico, which is actually a U.S. territory. And then in February of 2016, we got another case of local transmission, actually first sexual transmission in the United States. And then fast forward several months, Zika virus has been expanding in Central and South America. We've seen more travel-related cases in the United States. And we actually then in August got our first mosquito transmission in Florida, which Kelsey will talk a little bit more about in her section of the talk. But this is mostly localized to the Miami airport area. And then just to give you an idea of the numbers, this is data from the Center of Disease Control, the CDC, just from today, about how many cases we're getting that are locally acquired versus travel-related cases in the US and the US territories. And so most of, again, what we're seeing in the United States is travel-related cases, almost over 4,000 at this point. But the shocking number to me, and I think that's something that we don't really talk about much here, is that there are a ton of local acquired cases in our US territories, places like the Virgin Islands and Puerto Rico, which are really getting hit hard because of the fact that the mosquito populations there can carry Zika virus. And so the locally acquired cases is over 30,000 at this point. So something to think about going forward and why scientists are so invested on learning more about this virus and coming up with either a treatment or a vaccine for this outbreak. And so I've talked to you now for maybe almost over 15 minutes. And so I wanted to step back and give you guys a mini biology lesson as a teaser for Shirley's section, where she's going to get more into some of the virus biology, and just bring us back and talk about what exactly is the causative agent of this outbreak. It's a virus. And when I want to talk about viruses, I want to talk about their size, just to give you an idea of how small these little things are. And so when we think about us as humans, we're made up of 37 trillion cells on average. Of course, this is an average because when you're younger, you're of course made up of fewer cells. So if you think about dividing your cells up into 37 trillion pieces, that's how tiny a cell is. And that boils down to about 0.004 inches. And what does that actually mean? So if you think about 1 grain of salt, that's about 16 times bigger than a cell. And that's bigger than a skin cell, which is one of the bigger cells. Your blood cells are smaller than that. And so these cells are made up of 20,000 genes. And genes are the building blocks of our cells. So the genes are what determines that my hair is the color that it is, that my eyes are the color that they are, and also that I can go on my day-to-day life and live a healthy life. But when I get sick, whether it's a cold or a flu, some of my cells, those tiny cells, get infected with a virus. And so in order for a virus to fit into those cells, which are already 16 times smaller than a grain of salt, they are 100 times smaller than that. Really, really small. And so because they're so small, they need to be made up of even fewer number of genes. So most viruses are made up of between 4 and 200 genes. And so you think about how many things that we have to do in a day-to-day life. How in the world does a virus accomplish all the things to live with only 4 genes, or even only 200 genes? That's a lot less than our human cells have. And so the way they do this is because they need a host or a cell to live in. And so we're a wonderful host. Mosquitoes are a wonderful host, as Kelsey will talk about. And so to think about how they're taking advantage of cells in order to complete their day-to-day life, I also wanted to touch on the virus life cycle. So virus particle, and this virus particle has a couple different layers, and the outer layer is speckled with this pink image, which is a virus receptor. And the receptor is really important for the virus to identify what cell it needs to infect. And it sort of recognizes that, almost like how a barcode scanner recognizes a barcode, to attach and enter a cell. And so that's the first step of the virus life cycle, is to enter the cell. That step is called entry. So it attaches and enters. And then this pink squiggly thing that's drawn is actually the virus's genomic material, or DNA. So DNA is what makes up our cells, and viruses can be made up of DNA or even RNA. And so once the virus enters a cell, it needs to uncode. So it needs to take off its outer layer or its coat so that its genomic content or its DNA can enter the cell. And then once it's done with that encoding step, the next step of its life cycle is to replicate. And so replication is really important for the virus because then that's how it makes more of itself and lives to see another day. And so for a lot of viruses, they take advantage of the machinery that's already in our own cells in order to do this. Because if you only have 4 genes, you need some help from the host. And so that's how a lot of viruses take care of this replication part of their life cycle. And then once it's made more copies of DNA or RNA, and maybe more of these receptor proteins and more of its outer layers, it can then go through the process of assembly, which is when all of those parts come together and make a new virus. And then once all these new viruses have been made, they exit the cell through the egress step and then can start that whole life cycle again. And so I hope that those lessons are clear to you guys, and they'll serve as a sort of teaser for Shirley's section when she talks more about how viruses can transmit between cell to cell or between person to person. And with that, that's the end of my section. I'll take any questions.
I have two questions about viruses specifically. I'm sure there's a big range, but approximately how many receptors does an average virus have on the outside surface?
So that definitely, I'll repeat the question, sorry. So the question is, I'm sure there's a range, how many on average receptors does a virus have on its surface? So this definitely varies by virus, and it also depends on sort of the symmetry of a virus. So I drew that virus as a round particle, but often viruses' outer layers are much more structured. They almost look like a soccer ball or have even more phases. And so oftentimes it's that symmetry that governs how many receptors it has. It could have 10, it could have 20, depending on how many vertices are in the structure that outer layer forms.
And does a host get infected to the point of being sick because the virus gets into the cell and it takes over completely right from the start, or because the host can't identify and destroy it fast enough? Which of those two extremes usually causes the infection to take place?
Yeah. Okay, so the question was, is it, when you get sick, is it the virus that's creating the symptoms of the sickness, or is it is it the...
Is it because the virus just takes over because it's not recognized at all, or does it take over because the mechanism of the cell doesn't recognize it fast enough? And so it's a sort of a battle between how fast can it get in and take over the machinery for replication versus how fast is it recognized and destroyed.
So the question,
just get right in there and go.
okay, so the question is sort of the speed. How is the virus either escaping our own immunity or being like sort of like a master in disguise, and the cell doesn't realize they're getting infected by a virus. So this again also depends on the virus. So the cool thing about like things like the flu, where you get a fever and symptoms like that, is actually not because the virus is causing the fever. It's actually because your body's immune system reacting to the virus is causing that fever, because most viruses don't like high body temperatures, and that would kill the virus. And so in some cases, it's actually your body's response to the virus that's causing the symptoms, and not actually the virus.
So you have that Zika was 1947, chilling out in Uganda. Yeah. And then in 2007, it went to that other island. What happened between that time?
Yeah, sure. So, the question is, Zika was first identified in Uganda in 1947, but then in 2007 we saw it in Micronesia, across the globe a little bit. And so what was happening in between then? So I didn't show you guys, but the dates that I showed you were sort of the big picture. If we think about when it was first discovered, the first epidemic, and then the first sort of the relevant one of today. But there's actually been a lot more cases of Zika in between all of those years. And it's interesting because most of the cases around 1947 were in that sort of Uganda, Africa area. But then there are more instances of Zika in the Polynesia, Micronesia area before around 2007. It's sort of popping across the world as time goes on. And Kel's going to talk about this a little bit more, but that has to do with like where the mosquitoes live that can carry this virus, and so that sort of governs the locations that it goes at that.
We're gonna have to move on.
Okay, yeah. Last question or
One more question.
one more?
Is Zika mutating as the spread goes on, or is it sort of the same thing? It's getting more.
So the question was, is Zika mutating? So my lab actually works a lot on that stuff, And I think the data is been difficult to generate to get samples from human patients because Zika is found at such low levels in patients, and so I think we're still starting to untangle that. Stand by.
My name is Shirley, and I'm going to delve into virus transmission in particular to try and understand how would you get an infection like the Zika virus or like some of the other viruses that have been mentioned. And so far, we've already talked about Zika, which is transmitted by mosquitoes. So you can get infected when you get bit by a mosquito. But we've also talked about how Zika can be sexually transmitted. So that's already two different types of transmission and two things you have to think about when trying to avoid getting an infection like Zika. At the same time, we're right in the middle of flu season. So you may have been hearing about covering your mouth when you sneeze or covering your nose when you sneeze to try to prevent transmission that way, or washing your hands or avoiding to share utensils and food. And so that sort of implies a totally different type of transmission that's not related to mosquitoes or sexual transmission. And so this sort of underscores the idea that different viruses, as we talked about, they're all very different and they can be transmitted in very different ways. And understanding how they're transmitted is really key to both protecting yourself, but also if you think about it on a much bigger scale, how can we prevent it from spreading throughout entire populations and causing these big outbreaks that become really problematic? So I'm going to spend this section talking about a few specific types of transmission and the types of viruses that are spread in these ways to try to understand what you can do to protect yourself and why certain diseases cause outbreaks and others don't. So I'm going to first start with airborne transmission. And I'm starting with this because I think it's the scariest type of transmission, and I think probably most of you would agree. And the key to airborne transmission is it means that when a person who's infected sneezes or otherwise releases droplets that may contain virus into the air, they can sort of stay in the air for a long period of time and can just be breathed in by somebody else, and that person can be infected. So that's really scary. The good news is that very few viruses are transmitted this way. This is an example of 3 viruses that are transmitted, and these are actually basically the only viruses that we know of that are transmitted in an airborne way. So luckily, it's not a huge problem. And these viruses are influenza A, which causes the flu, measles, and chickenpox. I also put tuberculosis up there because you might have heard of that because of the coughing. It's not a virus, so I'm not really going to talk about it, but it is transmitted in a very similar way. And so trying to understand airborne transmission, we can sort of observe what it is about these viruses that might be related to how they're transmitted. And there's 2 key characteristics of airborne transmitted viruses. The first is that we observe that these types of viruses tend to replicate in the upper respiratory tract, and I'll talk about that in a second. But the idea is that they spend that whole replication part of their life cycle in cells in your respiratory tract. This is the really key part, is that the virus particles have to be able to become aerosolized. I'll also talk about that. So the first part, I'm showing a small virus particle. Looks a little bit like what a flu virus might look like. And so this viral particle has to find your upper respiratory tract, which is sort of the upper part of your breathing mechanism. So your nose, your mouth, the back of your throat. And I'm going to use flu as an example because it has a very well characterized mechanism for how this happens. So I'm showing a step of the life cycle that Catherine showed earlier. And this is the part where the virus has to find and attach to the cell using its receptors. And so if we look at a flu virus in particular, we can see that the little pink things, those little pink proteins on the outside that Catherine mentioned, have a name in flu, and those are the hemagglutinin proteins. There's also another protein on the outside of this kind of virus, shown in blue, and that's called neuraminidase. And I wanted to point out both of those proteins because you may have heard of different strains of flu like H1N1 or H3N2 or H5N1. And when you hear those strains, that's because they're talking about the types of the HA and the NA proteins. So H1 is a certain type of hemagglutinin protein, and N1 is a certain type of neuraminidase. So when you hear about H1N1, you can now think about the different types of proteins on the outside of the cell. But for the purposes of this talk, I'm just going to focus on hemagglutinin. And the reason I'm going to focus on the HA protein is because it has this really well-characterized interaction with a molecule called sialic acid. And what this means is it really likes to bind to sialic acid. So whenever it finds a cell that has sialic acid on the outside, it will bind to it and infect that cell. And if we look more closely, we actually observe that sialic acid is found on the membranes of cells in your upper respiratory tract. So when the flu virus comes into your body, it immediately wants to find and attach to those cells in your upper respiratory tract and not necessarily in the rest of your body. So when the virus particle comes close to the cell membrane and it has this matching receptor and molecule, it will bind and then start the process of entry and start the whole life cycle that Catherine talked about. And viruses like chickenpox and measles, though they don't have quite the same well-characterized mechanism, we expect that they have a similar sort of preference for these upper respiratory tract cells, which is probably related to how they are removed from the body through sneezing and coughing. The other really, really key point of why viruses are airborne is that the particles must be able to be aerosolized. And so when I say aerosol, what you've seen probably in your daily life is spray cans and other things that we call aerosols. And when we talk about those kinds of aerosols, we're talking about really, really fine particles that are usually pushed out using some sort of pressure system. And when we talk about viruses, it's really the same thing, where in this case, your body, when you cough, is pushing out really small particles. But not all viruses can be transmitted this way. And that's because these viruses have to be able to be really small. So normally, when you sneeze, and you may release a few droplets that may contain virus particles, the droplets will sink to the floor or sink to wherever is below you because the droplets are heavy and they get pulled down. For some viruses, however, they form really, really small droplets and particles, so they're able to sort of float in the air. We usually say that viruses that form particles that are smaller than 5 microns, which is about 200 times smaller than a millimeter, so it's really small, these are exceptionally small viruses, are able to do this. But not only do they have to be very small, these viruses have to be able to live outside a human body for a substantial period of time. And we know that viruses have to replicate in a host cell, so it's actually somewhat uncommon for viruses to be able to live outside the body for a long period of time. So that's probably why airborne viruses are so rare and why we don't see a lot of them. So the obvious question is, how do I protect myself from airborne viruses, since they could just be floating out in the air and I won't even see them? And the answer is really just some basic advice of washing your hands in case you touch one, so that in case your hand comes towards your mouth and nose, you decrease the chance of transmission. And just in general, if someone with the flu stays home, they're much less likely to infect anybody else. The other really key part of this, though, is vaccination. All of the viruses that I mentioned that are transmitted in airborne manner have vaccines, like measles vaccine, a flu vaccine, a chickenpox vaccine. And so the reason why we have vaccines for these viruses is because they have such a high potential to cause big outbreaks. So a lot of research was done early on when we started developing vaccines to make sure that we can protect people from these viruses. With that, I'm going to take a small break for questions, and then I'm going to talk about a couple other types of transmission. All right.
So for the airborne viruses that are under 5 microns, the ones that what is the PTA effect for the sake?
Great question. So the question was basically how long can these really small virus particles stay in the air? I think in general the answer is we're not exactly sure. There have been a lot of studies, especially on measles and flu. We think it may be from a few hours to a few days, but it really depends. There have been some recent studies on measles trying to identify it on surfaces, and we think that it can survive on surfaces for several hours to maybe a day, but we don't have like an exact number for that on that.
How easy is it for a larger virus to mutate and be small enough to be aerosolizable?
The question was how easy it is for a larger virus to mutate and become small enough to be aerosolized. And that's a really common question because airborne viruses are so scary. And it's just so much of the virus is related to how it's transmitted. So many different components are related to that. We don't even understand them all. So the difference between different types of transmission is actually a lot of changes. And so it's really, really unlikely. And basically, like, by the time a virus mutated enough that it was transmitted in a different way, we probably wouldn't even call it the same virus anymore. So it's really not something we worry about in an outbreak scenario. It's too different.
You said that as soon as like an influenza virus enters the body, it wants to find its acid, it wants to find its way to your upper respiratory system. But just for those of us who aren't scientists, clearly like something so small can't want anything or have any desires. So when we use language like that, like it wants to do this, what do we actually mean?
That's a great question. So the audience member is wondering, when I say want, like a virus wants to bind to something, what does that actually mean? Because the virus clearly doesn't have desires. It's a great question. I sometimes catch myself using language that doesn't make sense at all. So the idea is that the receptors on the outside of the influenza virus, for example, have a particular affinity for another molecule, which means that it's easy for them to bind to that other molecule, doesn't take a lot of energy. It's like a really good reaction. You don't need like you may have learned in chemistry class, like some reactions need extra energy or a catalyst to happen. There are certain molecules for which you don't need that, so it's very easy. So you imagine if you just put a virus particle in a pool of different molecules, more often than not, it's going to bind to the thing that it's easiest and most energy efficient to bind to.
So does it basically just wander around aimlessly until it finds its best match for finding?
So does the virus wander around aimlessly till it finds its best match? That's something that I think we're really still trying to understand, because these viruses, even though they have a preference for certain cells, we also find them in the blood and other places in your body. So an active part of virology research is trying to understand why viruses stay in certain parts of the body, why we find them there, why they replicate there.
One more question.
One more in the back.
I forgot the dimensions already, but when you talk about aerosolized viruses, do you mean the virus is really in the air, bare, so to speak, as opposed to dissolved in a water droplet that's floating around?
Yeah, so when the question is, when we talk about aerosols and viruses, is it just like a virus particle in the air, or is it in a water droplet or something like that? And that's a great question. So it can basically happen in two forms. One is when it attaches to like a droplet, but what happens when you release a really small droplet into the air is it dries. So we talk about how these virus particles are sort of on droplet nuclei. So usually on a like speck of dust or something that's inside of a droplet, or it can just be even without the droplet if it managed to attach to like a small particle or a dust that can float through the air. So it's not usually just the virus particle itself. All right, I'm going to continue with a few other types of transmission, and I'll get to the exciting viruses like Ebola and Zika at this part. The next type of transmission that I want to talk about is direct contact transmission. I really like the kissing fish. And I put that up there because you may have heard of mononucleosis, otherwise known as the kissing disease, because it's really easily transmitted through kissing. There are other types of direct contact transmission, some diseases, some viruses that cause much more serious diseases, like Ebola and HIV. The key to direct contact transmission is not that you actually just touch another person with the virus. It's not that kind of direct contact. It's specifically when a fluid, specifically blood or mucus inside a person, comes into contact with a fluid containing a virus of an infected person. So it's actually a pretty specific type of contact between two fluids. So more specifically, if you have your mucous membrane, which is what lines the cavities of your body, the openings of your body, like your mouth and your nose, or blood, comes into contact with some fluid that has the virus. And I'll talk about which fluids have virus in a second. So you can imagine there are a few different ways that this can happen. As we discussed with Zika, this can happen when a mother is carrying a child. There's a lot of fluid mixing between the mother and the child. It can also happen sexual transmission, or any other activity that involves needles or blood being passed from one person to another. So then the question becomes, why are some viruses, for example, HIV, transmitted primarily via blood, while others, like mono, are mostly through saliva and kissing? And that has to do with the types of fluids that actually contain and can transmit a virus. So this is a list of a few fluids that are in your body that could contain virus. Blood, saliva, tears, etc. And in order to determine for a particular infection which fluids can contain a virus, we can actually take an infected person, take some of each of these fluids, and see if we can grow them in a lab. So grow the virus, in a lab. So we take, let's say, blood, for example, and we see just using the blood as a starting point, no other source of virus, does the virus replicate in cells that we give it? And that gives us an idea of if that fluid can contain and transmit a virus. So for example, when we look at Ebola, we see that there are actually several fluids that can contain and transmit this virus. Blood is something you may have heard of that's important to Ebola transmission, but it's also transmitted by urine and by semen. I have saliva in parentheses because it's possible to isolate the virus in a lab setting, but there have been no cases of enough saliva being transmitted from person to person to actually cause transmission. So you can't actually get Ebola from like kissing or sharing like utensils and things. So that's good. And we also can look at these fluids over time. Usually your symptoms go away when your virus is not in your blood anymore, but you can see that in some of these other fluids, we can observe the virus many, many days post-infection. So it's not just about knowing if the virus can carry, if the fluid can carry the virus, but also knowing how long you might be infectious. There are some new studies that just came out about Ebola, where they're observing that semen actually contains the Ebola virus up to almost 500 days after the symptoms go away. So it gives us a lot to think about in terms of preventing outbreaks and preventing transmission. Just to compare Ebola to some other viruses, blood is bolded here because it's the main fluid that transmits Ebola. We also see the same thing in HIV, but you can see in HIV that blood and to some extent semen are basically the only fluids that carry this virus. And in contrast, we can look at mono, which is primarily transmitted through saliva, though it's also found in blood and semen. So the question becomes, why are certain viruses have preference for certain fluids? Why is it that mono can be transmitted by saliva, but other viruses can't? And that's actually it's still an open question in biology. We don't really understand why certain fluids tend to transmit certain viruses. One possibility is that we just observe the easiest form of transmission. For example, you probably come in contact to other people's saliva by sharing food, by sharing glasses, much more often than you come in contact with another person's blood. So it might be possible that for mono, it can be easily transmitted by many types of fluid, but we see the saliva transmission most often. We really don't know. But just to reiterate, and not to scare anyone. Ebola and HIV, not saliva, you can't get it by sharing food, but mono is spread this way. I still don't quite understand why. So I'm ending every section with how to protect yourself from these types of viruses that are transmitted this way. And as you've heard of, probably with Ebola virus, quarantining infectious individuals, making sure that their fluid can't be evolved is really good for diseases like Ebola, where fluid is a big part of the symptoms and it's very dangerous to handle, but maybe isn't so necessary for something like HIV, where it's circulating in your blood and doesn't need quarantining. That said, things like STD, education, and avoiding risky behaviors are the best way to avoid getting these types of viruses. I just wanted to end this section talking about this is an example of direct contact transmission. There's also transmission that we think of as indirect contact, which is sort of a subset. And it's the idea that it's the same sort of fluid from one person comes in contact with fluid from another person, but there can be an intermediate. So for something like mono, you have to be sort of actively sharing the glass because the monovirus is not going to stay on a glass or on a utensil for a long period of time. It won't survive. But there are viruses that can survive on things like forks or on tables for a longer period of time. One example of this is norovirus or Norwalk virus, that we hear about it a lot in association with food because it can survive on food and on utensils and things for much longer than other types of viruses. So that we call indirect contact transmission. So the ways to protect yourself and prevent outbreaks are very similar. I'm going to end this section coming full circle, coming back to vector-borne transmission because it's related to Zika, which I hope will serve as a good introduction for the next section, which is all about mosquitoes. The idea of vector-borne transmission is that instead of getting a virus directly from another person or from the air, you're getting it because you are bit by a vector, or a reservoir, which is an animal that can host the virus. The virus can live and replicate in this animal, but it might not actually kill or harm the animal in any way, and therefore the animal, such as a mosquito, can go around biting humans with the virus intact and therefore transmitting it. And Zika and West Nile virus are both transmitted by mosquitoes. I've put out malaria because it's probably the most well-known mosquito-transmitted disease. But again, malaria is not actually a virus, so I'm not going to talk about it. Another really common vector are ticks. So you may have heard of Lyme disease being really prevalent around here. Again, Lyme disease is not quite a virus, but still same type of transmission, the same principles apply. And the important thing to know about viruses that are transmitted by vectors is that the whole life cycle of the virus and the way that it's passed changes because now it can infect and involves two different hosts. So in the top left, you can see that an uninfected mosquito is biting an infected human, which actually infects the mosquito with the virus. Then that mosquito may go and bite a human who doesn't already have the virus, therefore infecting that human. So you can see that now the virus has to be able to live in two different hosts. And if you increase either population of infected mosquitoes or humans, you may get more of this type of transmission. So as we've discussed, Zika is transmitted this way, but some diseases such as Zika have an additional component of human-to-human transmission. So in addition to the mosquitoes causing infection, we also see infections passed between humans through sexual transmission and things like that. Protecting yourself from vector-borne viruses is very different, as you can imagine, from protecting yourself from other humans. And this is most important to understand where transmission is likely. Here I have a map of the Northeast United States, which is where Lyme disease is really prevalent. So knowing where certain types of diseases and certain types of vectors live. And also things like bug spray and protective clothing will provide an additional barrier from getting bit. That, I'll take a few questions, and then you'll hear everything you've always wanted to know about mosquitoes. Yeah.
I'm wondering if there are, what
quantity of a virus is necessary to infect someone, and if it differs a lot between the different transmission methods.
Yeah, the question was what quantity of a virus is needed to actually get infected and whether it depends on the transmission method. You guessed right, it does depend. The quantity we estimate can be as low as one virus. HIV can be transmitted by like one single virus, but many other infections need maybe 10-fold or 100-fold or 1,000-fold more viruses to cause an infection. We don't quite understand why. It has to do with the ease in which it can enter cells and the ease in which the immune system can recognize it and fight it off. So you may need a starting population of 1,000 for one of them to actually make it through and infect a cell. That's something that my lab did a lot of research on in terms of Ebola, like how many viruses do you need to get sick?
You had the chart, I think you had Ebola on you said it wasn't transmitted by tears or saliva was questionable. I'm trying to figure out like Ebola, I touch their blood and I wipe my eyes or would I then not get it? Or is it just not transmitted? I can receive it.
Yeah, so the question was, even though something like Ebola can't be transmitted by a fluid like tears, if you touch somebody's blood and then touch your eye or another fluid, then transmit it. And again, the answer to all these questions seems to be that it depends on the virus. For something like Ebola, we observed that transmission was happening more than we thought. So many times when someone was sick and a doctor who was really well prepared was taking care of them, they were still getting sick. So we actually think that it is possible for more types of transmission than we previously thought, but it really depends on how long Ebola can survive outside the body and how quickly that happens. Something like tears probably has a really low chance of transmission just because there's not a lot of fluid there. Also because your eyes are very isolated from the rest of your body. But for example, we don't know if you touch someone's blood and then lick your fingers and swallow them, that might have a higher chance of transmission. Which is why for things like Ebola, things like quarantine are really important.
In the earlier part of the talk, you emphasized the size of the particles that would be aerosolized, 5 microns. Is that cutoff size significant with respect to the other number, about 4 to 200 genes in the virus, so that for something to be down at 5 microns, that kind of puts an upper bound on how many genes it can load? Or?
Yeah, so the question is whether the size of the virus is related to the number of genes. And we've observed that it's more related to the shape and packaging of the virus. So we have some viruses that are very long and stringy and others that are really compact and small. So that's probably more related. I say that mostly because even though TB isn't a virus, it's like huge compared to viruses and it can be really small. So it probably has more to do with like the structure of the virus itself than the sheer number of genes.
Earlier you gave that list of viruses that can be airborne. I noticed the common cold wasn't on that list. Can the common cold be?
Can the common cold be airborne? It's actually not airborne. It's technically a direct contact transmission, and that's simply because it doesn't aerosolize. So you actually need the droplets. That said, if I am standing next to you and I sneeze on you and the droplets can very quickly enter your body, then you can get it that way. But the idea with aerosolized viruses is that they can hang in the air for a longer period of time. So if I sneeze and walk away and you're in the vicinity, you have a chance of getting sick. Whereas with the common cold, it's more like someone has to cough on you or sneeze on you.
So if you have the measles, I'm in trouble, but if you have the cold, I'm safe from you.
More safe. One more question.
I'm just wondering, for viruses that, as Catherine was talking about earlier, also infect primates as well as humans, And if they're not actively treated, they're either kind of population get like that.
Yeah, so the question is if the transmission of viruses in other animals like primates is similar. And yeah, a lot of the basic type of transmission is similar. Viruses do have a limited number of species that they can infect though, so not all viruses can infect both humans and primates. Some are specific to certain species. There definitely is worry that primate species could be wiped out by viruses. There's some evidence that some large ape populations in parts of Central Africa may have been greatly diminished in number by Ebola, because Ebola can infect primates as well. That's definitely a concern for us. Thank you very much.
All right, we'll do a brief intermission, about 8 minutes, let's say. And we also have sign up for a lab tour. There's only 15 spots that'll be leaving right from after this lecture, so please sign up during intermission if you want to do that.
Yeah, every time.
How do they get other sequencing?
I don't want to be on video. What's like the demographic breakdown of where you talk?
So it varies. Like I think in the past, especially for certain countries, we've had a lot of people over 30 and 40, but the system's been doing really well with Facebook alerts, especially which is awesome. I think tonight, especially, we have a lot of friends. I think mostly it's usually retiring age. I think we talk about retiring age and then also high school. There's a lot of teachers have been offering credit for that's so smart. Yeah, and that's just something like just organic that's happened. So we're actually looking to reach out more to high schoolers, high school teachers to make sure they know about us and offer that as an option to them. But then for fall lecture series, we do a tea ad, and that's how we get a lot of organic people coming and just they heard about us like that. But otherwise, our audience is obviously self-selected that enjoy science. But yeah, why do you ask? Oh, it's just we were just wondering. We're all in the same class. How did you guys hear about it?
With Shirley.
Well, she's great, and she's actually heading up DayCon next year, so our day-long science conference.
Yeah, I remember I put up some flyers for that.
Oh, good. Well,
This past spring. I was like, that's really familiar. Yeah.
Well, if you have friends that you think would enjoy this kind of thing, please do spread the word. If you have like ideas on how to better reach people who might be interested in this, we definitely live in a bubble, so it's easy to miss opportunities.
Yeah. I don't know. We did some experiences, but you said you aren't starting back up until next week.
Yeah, but I mean, like, we're definitely still trying to attract interest generally to our blog, and like Science by the Plane is for the most part year round. So,
You can come to DayCon. Yeah. That's the thing I put up posters for you.
Yeah.
Right?
I'm gonna run.
Yeah, I can help you on that. Is it a day or two?
Although usually she did the topic last year.
Oh yeah.
This is my roommate. Both of them. These are my roommates. Yeah, I was like, I recognize those figures. Yeah.
Nice. Cool. Yeah. Is DayCon here? Is it just like a full day?
Yeah, it's for Cambridge. Yeah. So even easier. You guys live in Cambridge. I feel very tall right here, but down here my face is
Yeah.
Okay.
Okay, everyone. Thanks for taking us out. I just want to say a couple things before we get started again. So in case you didn't hear stuff before, we are having a lab tour right after the lecture. And please sign up here if you have not done so already. There are 15 spots total, so that's all I got. Also, I want to plug our surveys. These are really, really important for us to get feedback from all of you. Let us know what you enjoyed about the talk and more importantly, what we can do to improve these types of events and future events. So please pull these out if you get a chance. You can just grab one after the lecture. There's a ton up here. I can bring some more up to the front. We really appreciate your feedback there. But I don't want to take any more away from Lucy's time, so I'll let her take it away.
Oh, yeah. Sorry. Alright, hi everybody, I'm Kelsey, and I work in a lab that studies mosquitoes and malaria actually. So we have thousands of these creatures flying around in a room not too far from here, in the lab where I work. So I'm going to talk to you today a little bit about mosquitoes and how they transmit diseases. And the second part of my talk is going to be focused on how we can stop them from transmitting these diseases. So first I'll tell you a little bit about the mosquito's life cycle. They begin their lives as aquatic larvae, and then after about a week or so, they emerge as mature adults. And these mature adults, like all other animals, have to mate in order to successfully reproduce as a species. But this mating event in mosquitoes is a little bit unique because the females of many mosquito species only have sex once in their life. And then after this single mating event, the female will store the sperm from that male and use it to fertilize her several egg batches that she can have during the course of her life. But she needs one more thing in order to develop her eggs, and that is your blood. So mosquitoes actually don't take your blood as their major food source. They use it for reproduction. And this means that the males, which of course don't develop eggs, are essentially harmless, and they don't bite people, so they don't contribute at all to the transmission of diseases. So as I said, these females can lay several batches of eggs, up to 7 during their lifetime, and each of these batches of eggs requires a new blood meal. So this means that the mosquito can bite up to 7 people throughout the course of their lives. And each time that this mosquito bites a person is an opportunity to either pick up or pass on a virus. But what actually happens when a mosquito bites a person that has a viral infection? Well, this virus is taken up with the blood meal and goes to the mosquito's gut, where the virus can begin to replicate, and then it needs to get out of the gut into the mosquito's circulatory system and get back to the salivary glands, where it can establish an infection. And all of this happens during the course of about a week. So if the mosquito survives for that week after it bites an infectious person, this virus will actually be transmitted, or at least every person that this mosquito bites will be exposed to this virus and may or may not develop an infection. But this process is obviously specific to certain viruses. For instance, HIV can also be present at high levels in human blood, but when it's taken up by mosquitoes, it just gets destroyed in the gut by the mosquito immune defenses, because HIV is not well equipped to survive in a mosquito environment. So another question that I've been asked a lot since I started working on mosquitoes is, why do they like humans so much? And the answer to this question is that they actually don't. And mosquitoes can bite anything from caterpillars to reptiles to other animals or mammals and birds as well. And not only do they bite these other animals, but they transmit diseases to these species too. So, for instance, you might see heartworm in your dogs, Eastern equine encephalitis, which is more common in New England, and avian malaria, which is driving birds like this Hawaiian honey creeper towards extinction. But of course, some species of mosquitoes do like to bite humans, and these are the most important mosquitoes in disease transmission. So every time a mosquito bites a human, as I said, is an opportunity for pathogen transmission, which means the more that mosquito prefers humans over other animals, the more that mosquito is likely to pass on a virus or another disease like a malaria parasite. So this first mosquito species here is the major vector of malaria, and there are up to 30 other species that can transmit malaria, but this one is so good at biting humans that it supports a large burden of malaria in Africa. The next mosquito
this Culex species is the main transmitter of West Nile. And this mosquito has preference for birds and humans, which means that it can act as a bridge between birds, where West Nile is carried as a reservoir, and between humans. Aedes aegypti is a mosquito that a lot of you will have heard about in the news in relation to the Zika outbreak. It's the major virus that contributes to the spread of Zika. And this mosquito takes over 90% of its blood meals from humans. So it is very strongly human-specific. In contrast to Aedes albopictus, which is a very similar mosquito that transmits all the same viruses, but it has a much lower preference for humans, which means that it contributes in a very minor way to the spread of these diseases. So Aedes mosquitoes, as Kat said before, are present in the US, and this map is from the CDC and shows areas in the states where there is potential for these mosquitoes to live, and that's based mostly off of the climate conditions. I want to show you this other map, which was also made by the CDC, which is more accurate in reflecting the abundance of mosquitoes in particular regions of the United States. So if you look at this map, it makes a little bit more sense for why Zika local transmission is happening in the southern tip of Florida and not so much in the surrounding areas. Because even though those mosquitoes are present at low levels and are capable of living there, they're really not that abundant across most of these southern states, as the other map might be. So as I said, Zika is locally transmitted only in Florida, and there are a couple other reasons for this area being a hotspot of transmission as well. For instance, there have been over 700 cases imported, largely from Puerto Rico, where there's a lot of ongoing Zika transmission. And so these 700 imported cases provide a large base population for the mosquitoes to bite and then transmit that disease to other people in the region. And another thing about why this maybe hasn't spread so far to other states is that mosquitoes actually do not travel very far over the course of their lifetime. Usually they stay within a 1 kilometer range, so it's not like you're going to get a mosquito who's infected with Zika in Florida flying all the way over to Texas or even up to Georgia to transmit Zika in those regions. So I'm going to pause for a minute for some questions. Yes?
Why is the Aedes, the mosquito population in the island of Hawaii so large, but the other islands of that state non-existent?
Let me go back to the map for a second. In Hawaii?
Well, the big island is all red and all the other islands are white.
Well, as I said, mosquitoes don't travel very far, so it's possible that they've just been on that one island for a long time and maybe were wiped out on the other islands. I'm not too familiar with maybe insecticide use in Hawaii that could have wiped out populations of mosquitoes that once existed there. Sorry, I'm not sure I have a better answer.
Sorry, I just maybe three.
Yeah. All right. Yes.
Have there been any attempts to maybe infect ourselves with something that would, in turn, infect the mosquitoes with something that would be fatal to their population and decrease their population, so we don't have as many problems with their transmission?
Yeah, that's a really interesting idea. So far, we haven't. Did you repeat the question? Oh yes, of course. Sorry. So the question is if there are any other agents infecting humans or that are present in humans that can cause fatality in mosquitoes after they bite us. And so there has been a little bit of research into this topic, and there aren't any viruses that we found that humans carry that have a fatal effect on mosquitoes, but there are agents like the drug ivermectin that if a human takes ivermectin, any mosquito that takes a blood meal from that human will die. So that is, yeah, it's a potential.
Is it transmittable from mosquito to mosquito though?
No.
Why are certain species
question, and it's definitely something we don't have. Oh, sorry. So the question is, if different mosquito species carry different diseases, what's the reason for this specificity? And we don't have a very good understanding of that. That's something that some people in my lab are actually working on. Yeah, there's a lining of the gut called the peritropic mucus, which prevents a lot of viral infections in some cases from making it through that lining. And so there's research into whether maybe that's thicker in certain species that are more refractory to viruses, but it's definitely ongoing.
One more question.
So you commented that the females take blood day of the infected person, the infection gets into their bloodstream. Does it also get into their baby's bloodstream as well, and are they then carriers?
So the question is, if the mosquito takes up blood that is infected and that virus, the mosquito's bloodstream, if that virus can also be passed on to the offspring of that mosquito. And the answer is, in very rare circumstances, yes, this can happen. It's been shown with dengue virus, but it's like a very low frequency, 1 in 1,000 times this might happen. I think that was my last question, but I can talk to you after the talk. All right. So the next part of my talk is going to be focused on intervention strategies against mosquitoes and disease transmission. So the method you will all be familiar with is the use of insecticides, but I'm sure you're also familiar with the limits of this technique, which include resistance and unwanted environmental effects. Some things you might be less familiar with is that localized uses of insecticides are also limited based on the mosquito's behavior of the species that you're trying to target. For instance, insecticide-treated bed nets and indoor residual spraying, which is spraying the inside walls of your house, these methods have been very effective against mosquitoes that transmit malaria. But insecticide-treated bed nets depend on mosquitoes biting at night. And the Aedes aegypti mosquito is very much a day biter. So treated bed nets are unlikely to be effective against Zika virus, for instance. Similarly, spraying the inside walls of your house depends on the behavior of that mosquito to bite indoors. But Aedes albopictus, the minor vector of Zika, is an outdoor biter. So in areas where Aedes albopictus is a problem, spraying the inside of your house is also going to be effective. So based on the limits of insecticides, there have been a lot of novel methods for mosquito control, and some of these are very innovative and are based on the release of large quantities of mosquitoes that have been altered in some way. So these alterations might be genes that cause sterility or lethality in these mosquitoes, and it could be traits that cause pathogen resistance in these mosquitoes, such that you can replace a pre-existing susceptible population of mosquitoes with one that is resistant to pathogens. So these release-based methods are all species-specific. That's because if you're releasing large numbers of one species of mosquito, that gene or trait that you put into those mosquitoes is incapable of crossing species barriers into other mosquitoes. So it's very good at targeting an individual vector. So I'm going to talk about 3 specific methods that involve release of mosquitoes. The first is genetically modified mosquitoes designed by a company called Oxitec. I'm also going to be talking about Wolbachia infected mosquitoes with a particular example of the extra gene drive. So Oxitec is a company that has designed mosquitoes to carry a gene that causes lethality. And the idea is that if you release enough males that carry this gene, they will outcompete the native population of males for mates, and then these females that mate with them will have progeny, but these progeny will die before they reach adulthood, and therefore will not contribute to disease transmission. And the males, because they also carry this will also die prematurely, usually about 48 hours after they're released. So it's a very short time period for this activity to occur. But this technique is focused on suppressing a population. It's self-limiting because it's, as I said, very short-lasting. So you have to continue to release these sterile mosquitoes if you want to continue the effects of suppression on that population. It's species-specific, and it's currently being used in Florida Keys, and it was also used in Brazil and the Cayman Islands, with what Oxitec claims to be a 90% efficient suppression of mosquito populations there. So next I'm going to talk about Wolbachia, and this is a very special bacterium that infects insects, and it alters them in such a way to convey pathogen resistance to these mosquitoes. So here we have an illustration of a Wolbachia infected mosquito biting a human infected with a virus like Zika. So this mosquito bites an infected person, but does not become infected itself, which means that when this mosquito bites somebody else, the virus will not be transmitted, leading to a break in the cycle of transmission. And this Wolbachia has been shown to be effective against dengue virus, chikungunya virus, Zika virus, and also malaria parasites, possibly, which is the project that I work on in my lab. So it's great that we have these Wolbachia-altered mosquitoes that are resistant to pathogens, but in order to actually use them for vector control, they need a way to spread into a population to replace the existing one. And it just so happens that Wolbachia comes with a built-in mechanism to do this. And this mechanism is called cytoplasmic incompatibility. So cytoplasmic incompatibility results in reproductive benefit for female mosquitoes that are infected with Wolbachia. And as you can see here with my green Wolbachia infected mosquitoes, the females that are infected can produce progeny with a male that is either also infected or uninfected. But if the female mosquito is not infected, she can only mate successfully with a male who is also uninfected. So this results in female mosquitoes that are infected with Wolbachia being able to produce, on average, twice as much progeny as females that are not infected with Wolbachia. And this allows the eventual takeover of Wolbachia-infected mosquitoes. Oops. So this is the population replacement strategy. It's self-sustaining because if you release enough females that are infected with Wolbachia into a population to begin with, they will take over and do the work themselves to continue that effect. It's species specific, and it's currently in use in Brazil and Colombia and Vietnam. So next I'm going to talk about gene drives. And gene drives are based on the principle that you can bias the inheritance of one gene over another gene. So typically, in your parent, you have two copies of one gene. And in this example, we have our gene of choice in red, and this gene of choice could convey something like sterility, lethality, or pathogen resistance. But this gene is only on one of two chromosomes, so it's only going to be inherited in 50% of the offspring of this parent, and the other 50% are going to get the normal copy. But in the case of gene drives, this gene of your choice has the ability to be copied over onto the other chromosome, which results in 100% of the offspring containing the gene of your choice. So I'm going to talk about a specific example of this, which is called X-Shredder. And in this example, we have male mosquitoes that carry this gene of our choice on the Y chromosome. And this gene, when it's expressed, results in the destruction of the X chromosome in the cells that contain this gene. But this only happens in the sperm precursors of this male. So this only happens in reproductive cells. So basically it results in any sperm that carry an X chromosome, they will be destroyed because the X chromosome is inviable. So the progeny of the males that carry this gene are all going to carry a Y chromosome. The sperm will all carry a Y chromosome, which means that all the progeny will be male. And all of these male progeny are also going to have this gene on their Y chromosome, which means that this will continue in the next generation and the generation after that, until essentially you have a mosquito population that is entirely composed of males, which is obviously unsustainable as a species. So this is a population suppression technique. It's self-sustaining because it propagates itself through population. It's species specific, but it is currently not in use. And neither are any other kinds of gene drives. That's because gene drives are controversial, particularly because of this ability to propagate themselves through a population. So there are currently methods being developed to limit the capacity of gene drives to propagate indefinitely. So these methods can act as sort of a brake or an undo button for the gene drives that you've released into the wild in case something unexpected and unwanted occurs down the line. But it has the potential to be immensely powerful in vector control. And it might have some of you thinking, what happens if we do get rid of an entire species of mosquitoes? So let's talk about the role of mosquitoes in the ecosystem for a second. Well, mosquitoes are pollinators. As I told you, blood is not their main food source. They actually eat nectar. And mosquitoes are also food for birds and bats. And in the larval stages, they're also eaten by fish. They eat organic pollutants in the water, which makes that water more hospitable for other organisms to live there. So they do have a role in the ecosystem. But this role can vary depending on the region that these mosquitoes live. For instance, in the Arctic, mosquitoes are a huge component of the insect species that can survive there. So their importance is probably more in the Arctic than, for instance, in the jungle, where there's so much biodiversity. There are so many other insect species that live there. So probably other insect species could compensate for a lack of mosquitoes. But I also want to emphasize that there are over 3,500 species of mosquitoes in the world. And those that can carry human diseases are less than 50. So even if we did get rid of all 50 mosquito species that are capable of transmitting disease to humans, we still would be nowhere close to the extinction of mosquitoes. And I also want to emphasize that the goal is not to exterminate mosquitoes, it's to reduce viral transmission. So you're not intending to wipe out mosquito populations. The goal is not to exterminate mosquito species. It's just to reduce the burden of disease. I want to leave you with some final thoughts after our talk today. So outbreaks like the Zika outbreak are a reason to be concerned and to inform yourself about the risks, but they're not a reason to panic. And there may be more opportunity in the globalized and urbanized world that we live in for the spread of viruses to occur. But we also have more tools to monitor the spread of viruses, and we have more tools to diagnose diseases and treat diseases and combat transmission. So the final message is to protect yourself and inform yourself, make intelligent decisions about your travel plans, and don't panic.
We can take 3 questions. Okay. Yes.
I was wondering if you've seen any Wolbachia resistance.
In mosquito, okay, so the question is if we've seen any resistance to the effects of Wolbachia in mosquitoes, and the answer is not yet. Though I will say that there are a lot of Wolbachia strains out there, and not all of them have the same effects as the ones that are used for the control of mosquitoes. But we haven't seen any reversal of the effects of Wolbachia. Yes?
Okay, so if the symptoms of the Zika, I don't know which one of the 3 of you, but if the symptoms of the Zika virus are
question, and if you guys want to jump in, go for it. Basically, Zika, the question is, if Zika is causing microcephaly in babies, but in adults it has more flu-like systems, what's sort of the reason in this relationship between symptoms? And, well, I guess Zika has a unique capacity to cross the barriers of the fetus. So that can result in all kinds of abnormalities in theory in the fetus because not many viruses are able to cross that barrier. So that's sort of the unique thing about Zika virus, but I couldn't tell you any relationship that might have with the flu-like symptoms.
I think there's a lot of unanswered questions. We do know now that Zika can cross the placental barrier. An important note that I think the field is also looking at is the cases in microcephaly are actually much higher in northern Brazil, which is where the outbreak first started, than in any other region. We're seeing actually less microcephaly in cases in the United States. And so there's potentially other factors, such as human genetics or other environmental conditions in the region where we're seeing these cases. So that's an active area of research.
Has the gene drive procedure been implemented in any other area of infectious disease, or is that still just on a trial as well?
In infectious diseases, definitely. Oh, the question is, are gene drives implemented in any other areas of research other than infectious disease? And so they haven't been applied to infectious diseases yet. I think the only use that I know of them in like agricultural areas is there are some mushrooms that have been altered with the gene drive to take away their capacity to turn around, basically. And I think that's the only application that I know of. That's.
Well, thank you so much. If you're interested in the tour, please meet down here before they'll leave. Oh, yeah. Yeah. You'll be fine. When you guys oh, thank you, dude. Could you do me a favor and unplug both of the things that are plugged in down there?
Wait, just like straight, like I'll just like from.
Yeah, just unplug everything. Okay. Bye.
Bye.
I hope you
See you
enjoy.
next fall. You're gonna be here next fall, right?
I won't actually.
You're not leaving.
Well,
You're graduating or any of that stuff.
Well, not quite yet, but I've been co-director for 2 years now.
Well, you're just gonna hang with it.
Yeah.
You're just sitting your stride. Katie will be ready in about another 2-3 years.
Yeah. Well, yeah. You'll be in good hands. I'll probably provide for at least one semester, and I think.
Great.
Yeah.
We might have a little more love for Katie on the margaritas.
She might be more like knowledgeable about that than I am.
All right.
All right.
Well, thank you so much.
Oh, yes.
Any association between me and Harvard Medical School which does not involve breaking and entering would be
Yeah.
a real source of pride to my mother. So,
Right.
thanks.
Have a good holiday.
Thank you. Have a thanks.
They do a lot of they work like. Oh yeah, no, it's still like she's still very much focused on the retina. I actually worked on when I was doing rotation when I first started, and I collaborated with her lab and they work on the retina as well. I'm just totally. I think this is Well, that's gonna be.
As a unit, as a group, in the
I should. So these are actually the coordinators of science in the news in general. So you should, yeah. He was just speaking the praises of science in the news.
Oh,
so,
great.
Yes.
Thank you. Yeah.
Both of those.
Yeah.
Yeah.
In the past, there's been sometimes there's been.
Yes.
I know this is a small amount
No,
of
thank you
funding,
so
but
much.
at least it'll buy some cookies for the next one.
Really appreciate
Well,
it.
you're welcome.
Thank you
So
so
it's
much.
a great program and
Yeah, we hope to, we've been, this is our 16th or 17th fall series.
Right.
So, yeah, we're hoping to keep going strong. So,
Please do.
Yeah.
Excellent.
Yeah. Yeah. Thank you so much.
You're welcome.
Can I take this? Yeah, I think we can close it. Yeah. Oh my god.